Hello everyone. In this video, I'm going to go over some applications and the scientific notation, some application problems with numbers. So I put some examples directly in here that you may check. The scientific notation is that's like the preliminaries for working with the numbers. The scientific notation is simply writing the number with possible powers of 10 where the coefficient of this power of 10 is a number between 1 and 10, 1 and 10. So here are some examples. For example, 0.00234, this is not a scientific notation, but you may move this decimal point 3 to the right to make it 2.34. In that case, since you move that decimal point 3 to the right, that becomes 2.34 times 10 to the negative 3. See, this is the scientific notation of this number, 0.00234. It kind of shows you the magnitude of the number as powers of 10. So this is the same thing. I have like 10,156.29. You move the decimal point this time to the left because this is a number bigger than 1. So you move to the left 5 decimal places, five like digits to the left. Then I got 1.015629 times 10 to the 4. That shows like the magnitude of the number. So we may work with any kind of quantity and write it as in scientific notation. For example, here in this example, you have 340 gigabytes. Giga means 10 to the 9. It's a billion. So, and 340 is 3.4 times 10 squared. And you multiply them and you got 3.4 times 10 to the 11. So that's the scientific notation for 340 gigabytes. So this scientific notation really makes your calculations easy and shows the magnitude of that number. Here's another example. You can always like pause the video and check it. So this is like 0.000001. You move the decimal point 6 to the right, so that makes it 10 to the negative 6 times 1. You don't really need to write this one, but it's good to show in that notation. And here are some computations with the scientific notation, and the order of magnitude is about this powers of 10. It shows the size, the magnitude of the number. Let me just pause the video and check these examples. See, these are simple multiplication and division problems. You simply estimate them because the problem says estimate, and then you simply do it without a calculator. See, like doing it really quickly. 5 times 10 to the 6 times 2 times 10 to the 3. That's like 10 times 10 to the 9, which is 10 to the 10. See, it's easy to do those computations because of powers of 10. And here are 3 examples in which really assumptions are kind of not given, but it's like an open-ended question. If the assumption is given, then you can easily do it mathematically. Otherwise, you have to do some assumptions. Like for example, the number of steps you take in an average day. Somebody can say, "Hey, I'm simply taking like 4,000 steps on average." For example, myself taking like 7,000 steps. So that really depends on what simply your specific situation is. But this is how you work with all these numbers. So you can easily do this for you, and these problems really can be solved by assumptions. So the assumptions needs to be given to you, whenever you work with these problems. But they're like simple style problems. Now, the major application problems of this section here are these energy problems. So I'm going to start with this first problem. Maybe you can pause and check. I have like 3 problems in here. And let's start with number 1. So it says, how many liters of oil are required to supply the electrical energy needs of an average home for a month? So I put some like problem numbers in here that which equations you will use. Now you see you want to figure out the liters of oil, so that needs to be your outcome, and the energy needs of an average home for a month. So if you look at here, it says the electrical energy used in an average home daily. So if you look at the energy needed in this case, so it's like the energy needed in this case, that's going to be 30 times 5 times 10 to the 7 joules. That's like the energy unit. So it's going to be 150 times 10 to the 7 joules. So this is really the needed energy for a month. And you want to convert it into liters of oil. So now if you look at the amount of energy released by 1 liter of oil, it's 1.2 times 10 to the 7. So that means like 1 liter oil is equal to this much energy. So I can write this fraction, which says 1.2 times, I'm sorry, I'm going to write it in a different order because I want to convert it into liters of oil. So 1 liters of oil produces an energy of 1.2 times 10 to the 7 joules. See, this fraction is equal to 1 because they represent the same thing. Like that energy amount of 1 liter of oil is same as 1.2 times 10 to the 7 joules. So they're equal. Why do I write it in this form? You can flip it. They represent all the same kind of ratio. But I want to get the outcome as liters of oil. That's what I'm really looking for. So here, as you see, if you write it in this form, the joules will cancel, and you will get the answer in terms of liters of oil. And 10 to the 7 will cancel, so I need to just find 150 divided by 1.2, and now the outcome unit will be liters of oil. So I got, if you divide those two in a calculator, I got 125. It's like 125 liters of oil is needed to supply the energy of an average home for a month. So that's how you solve this problem. And all the remaining problems in this section works in, just work in the same way. Like for example, compare the energy released by burning 1 liter of oil and by the fusion of hydrogen in 1 liter of water. So they're given in here. If you look at that one, the oil, it's given to be 1.2 times 10 to the 7. And what about 1 liter of water? And by fusion, it's given to be 6.9 times 10 to the 13. So let's compare them. I have 6.9 times 10 to the 13 joules, and then I divide it by 1.2 times 10 to the 7 joules. So this first one is the energy released by the fusion. Okay, this one is the energy released by 1 liter of oil. So I compare them. So I'm going to try to figure out how many times one is the energy. If you look at that, 10 to the 13, 10 to the 7, we got 10 to the 6, right? Times, if you divide 6.9 and 1.2, I got like 5.75. See, if you write it in the normal form, the standard form, 1, 2, 3, 4, 5, 6, so you got like 5.75 and then 4 zeros. So it's like almost 6 million times of whatever released from 1 liter of oil. So it's like that much bigger. So see, like you just say it's like times bigger. That's how you get this number. See, I compared the two numbers. So I hope this problem is clear. So you see, you compared two energy amounts from fusion and 1 liter of oil. Now, the next one is if you could generate energy by fusion, the hydrogen and water, it's the same thing. How much water would you need to generate the electrical energy used daily by a typical home? Remember, daily, you need, it was 5 times 10 to the 7 joules, right? This is what you need um, this is the energy needs of a home daily. And then what about from fusion of hydrogen? You get an amount of 6.9 times 10 to the 13 joules. This is obtained by 1 liter of water, right? From 1 liter of water, you obtain this much energy. So let's see that we have what we need is 5 times 10 to the 7 joules, and we want to find how much water we need to obtain this much energy. 5 times 10 to the 7, so that's going to be 1 liter of water is equivalent to 6.9 times 10 to the 13 joules. Now, this fraction again, as I said, this fraction is simply 1 because that's the amount of energy released by 1 liter of water when you do the fusion of the hydrogen. So the joules again will cancel. See, you get the amount of water, and so we got something like that, 5 over 6.9 times 10 to the 7 divided by 10 to the 13 liters of water. So that's the water amount that we need. See, I mean, folks, be careful. You're simply converting the energy unit into the amount of water, because that's what you need to find how much water I need. And if you simplify, this is going to be 0.725 times 10 to the negative 6. That's a really small amount. So we write this is going to be 0.1, 2, 3, 4, 5, 6, 7, 25 liters. I'm pretty sure this is less than a drop. It's a really small amount of water is what you need. So that's how much energy released by fusion of hydrogen in water. So yeah, these are energy type problems. As you see, you simply convert one unit into another, and I hope these examples are clear. Now I want you to try this problem. Problem at the bottom, it's an interesting problem. It says how much energy, like let's say you can capture the energy released by sun for just 1 second. I mean, just the question is like, how many years you can use this as an energy supply for the US. It's kind of like a really interesting problem. And here, if you look at the table, in the table, it shows the annual energy generation of sun. It's 1 times 10 to the 34, and the energy needed by US for a year is 1 times 10 to the 20. But this is annual. So it's like yearly energy release. You need to convert it into seconds first. And then find the amount of energy released by sun in a second. So let me, you can pause the video here and then try this problem. And be careful, let me just put that here as well. So it's like you're going to be using 1 times 10 to the 34 and 1 times 10 to the 20. Can check this. Yeah, now if you look at the solution in here, I already worked that out. You simply first convert 1 year into seconds, because you need to find the energy released by sun per second. So you convert this 10 to the 4 joules per year to the amount of joules per second. So you got 0.31 10 to the 27. So that's the amount of energy released by sun per second. And you want to convert this into the amount of years. In 1 year in US, you're going to be using 10 to the 20. So that will be, folks, good for more than 3 million years. Wow, that's so amazing. So if you can capture the energy released by sun for 1 second, that will be good enough for the energy supplies of US for more than 3 million years. Well, that's interesting. Yeah, that's kind of like the value of the sun. Now, the next part is how you do the scale ratios. Folks, in scale ratios, they're really simple. If you want to write the scale ratio, you have to just put the same unit in there. It should be like the same unit. For example, here I have 10 miles, right? I have to convert this into inches because I have 1 inch on the map. So 1 mile is 5,280 feet. It's just 1 mile. So miles will cancel. Now I got feet, and times it by, like 1 feet is simply 12 inches. So feet will cancel as well. If you multiply all of them, you got 633,600 inches. So that's the amount of inches in 10 miles. So the scale ratio for this problem will be 633,600 to 1. That's the scale ratio of this map. So you need to convert the units into the same smaller unit. It's like inches, you convert all of them into inches, and then that will give you the scale ratio. It's kind of like, that means in reality 633,600 inches showed by only 1 inch on the map. That's like the scale ratio. And here, this is a try problem. You can pause the video and try. And here's the solution. You may just check the solution in here. It's not that tough. And guys, I have 2 more problems, and one is like a try problem again. So this is a nice one. It's like that typical type of problem. The distance that you want to travel is 4.1 times 10 to the 13 kilometers, and you want to convert this into hours, and your spaceship goes with 50,000 kilometers per hour. So in 1 hour, see, I'm converting this into hours. In 1 hour, your spaceship can go 5 times 10 to the 4 kilometers. See, this is the distance that you want to cover, and in 1 hour you can travel 5 times 10 to the 4 kilometers. See, this is kind of that unit analysis. The kilometers will cancel, and you're going to get the number of hours that you will spend for this trip. So in that case, you will get, this is like 10 to the 13, 10 to the 9, and from here you got almost like 0.8. So it's like 0.8 times 10 to the 9 hours. And this is like 8, you can just see 80 million hours. And you can do a simple calculation. This one is like approximately 100,000 years. You can really do like a small calculation, like 1 year is simply 365 times 24, which is 8,760 hours. So you're going to divide it by that. So it's like a little bit less than that, but still it's around like 100,000 years. So that takes that much with the fastest spaceship, and you're going to the closest star system. So it's so interesting. So we have a long way to go. And I hope that example is clear as well. And the final example is a try example. And you can check this problem. Like, it's kind of like the kind of like the age of Earth is 4.5 billion years, and the human history is like 10,000 years. So let's say you try to represent the entire history of Earth with a 100-meter long timeline. So it's kind of like 4.5 billion years is represented by 100 meters. And the question is this: what distance really represents 1 billion years? In one problem, you can pause and check this now. Work on this problem now. And of course here you can, as you can see, you're simply converting this in this problem. You're simply converting the number of years, which is 1 billion years, into meters, and 100 meters represents 4.5 billion. So So that makes 22.2 meters. So that much on this timeline represents, be careful, the whole timeline is 100 meters. That represents 22.2 meters. And of course, like a natural question, how long will the human history be on this timeline? So in that case, you will change this 1 billion years into 10,000 years. Can you check that quickly? Try this problem. So yeah, 10,000 years is 10 to the 4. So instead of here 10 to the 9, you're going to replace this by 10 to the 4. So that will give you an interesting observation. I will give you 22.2 times 10 to the negative 5, because you have 10 to the 4 over 10 to the 9, 10 to the negative 5. So that will be only 0.22 millimeters. It's that small. If you look at the whole history of history of human. So I hope these examples are clear. Thanks for watching. Bye.